In this tutorial, I will show the most basic connection, the serial connection. Later, there will be videos where I will explain parallel and mixed connections. A serial connection happens when we connect components side by side. There is only one path through which electrons can flow in this connection. Thus, the same current flows through all circuit elements connected in series. Resistance is defined as the difficulty shown against current. A resistor is a circuit element that makes it difficult for electrons to pass. Its unit is ohm. Resistors are indicated by the letter R in circuit. Each circuit element has a certain resistance. By simply adding up all the resistances in series circuits, we find the total resistance of the circuit. If we refer to the resistors here as R1, R2, and R3, the total resistance will be R1 plus R2 plus R3. Total resistance is shown as RT. It is very easy to calculate the total value of the resistors connected in series. It is sufficient to sum the value of each resistor by writing them side by side. For example, suppose there is a single resistor circuit connected to the power supply. Let its value be 5 ohms. What is the total resistance of this circuit? It's very easy to find. Since there is only one resistor, the total resistance will also be 5 ohms. If we add a second 10 ohm resistor R2 in series with this resistor, what will be the total resistance? In this case, the total resistance will be 15 ohms, the sum of the two. Let's add another 20 ohm resistor R3. The total resistance will be R1 plus R2 plus R3. From the 5 ohm plus 10 ohm plus 20 ohm operation, the total resistance will be 35 ohms. Normally, the wires connecting the resistors also show resistance. But this resistance value can be neglected because it is very small. We can understand the resistance values by looking at the color codes on the resistors. If you wish, you can look at how the resistor color codes are read later. Now, let's look at how to find current in series-connected resistors. According to Ohm's law, current is found by dividing voltage by resistance. If we express them with the letters in which they are shown in the circuit, it will be I equals V over R. Let's look at our examples where we will calculate current according to this formula. We definitely use these triangle transformations in Ohm's law. When finding the current, we divide the voltage value by the resistance value. In this formula, we can see that the current is multiplied by the resistance to find the voltage, and another is to divide voltage by current to find resistance. They all come from a single formula. We can easily see whether we should divide or multiply by covering the value we will find, expressed in terms of each other only. In the future, we will deal with the use of these formulas. We defined resistance as the difficulty shown against the current. So, the larger the resistance, the smaller the current will be. The current for this circuit will be 0.3 amps from the result of 1.5 volts divided by 5 ohms. For this circuit, where two resistors are connected in series, the current will be 0.1 amps as a result of 1.5 volts divided by 15 ohms. For this circuit, where three resistors are connected in series, the current will be approximately 0.04 amps from the result of 1.5 volts divided by 35 ohms. We were able to find the current value when we divided the voltage value of the power supply by the total resistance value. We have seen that the current value decreases as the resistance value increases. We can find the same result by measuring the current flowing through the circuit with the help of a multimeter. In the ammeter function, when we connect the multimeter in series with the circuit, we can measure the value of 0.3 amps. This example will be very useful for us to understand the relationship between resistance and current. The current that an LED must flow through in order to give light without being damaged is around 30 milliamps. If it's too low, it will not light. If it is too high, it will explode and be damaged. Let's connect a 10 ohm series resistor to the LED in the circuit here. The LED will glow very bright at first and then explode. Because when we calculate the current passing through the circuit, it will be approximately 900 milliamps from 9 volts divided by 10 ohms. Since this current is too high for the LED, it is damaged. But if we connect a 330 ohm resistor to this circuit, the current will be about 27 milliamps. This current is a suitable current for the LED to work properly. If we increase the value of the voltage source, we need to choose the appropriate resistor with this principle. Here, some voltage is also consumed on the LED, but I did the calculation by ignoring it. It is also worth noting that. In series-connected circuits, the same current flows through all circuit elements. We must not forget this. Because there is only one path for the current to flow, and this current has to be the same at every point. When we connect the batteries in series, we get higher voltages. When we connect two 1.5 batteries in series, we get 3 volts. And when we connect 3 batteries in series, we get 4.5 volts. Now let's look at how to find the voltage in series-connected circuits. If there is only one resistor in the circuit, the voltage across this resistor will be equal to the source voltage. The voltage across this resistor will be 1.5 volts. What if there are 2 resistors? First, we need to calculate the total resistance. Here, the total resistance value is 15 ohms from the sum of 5 ohms plus 10 ohms. The current value is 0.6 amps from 9 volts divided by 15 ohms. We know that the same current flows through all resistors in series circuits. Then, we can find the voltage across resistor R1 as 3 volts from the formula IR1. In the same way, we can find the current across resistor R2 as 6 volts from the formula IR2. Here we can see that the voltages of the resistors are proportional to the resistance values. A 5 ohm resistor consumes 3 volts, while a 10 ohm resistor consumes 6 volts. Even if more resistors were connected in series, we would have to calculate in the same way. We can calculate the voltages on the resistor in this way without finding the current value. In addition, the total voltage consumed by the 2 resistors gives the source voltage. Otherwise, we would have miscalculated. This is the working principle of series-connected circuits. I hope this lesson was helpful and you liked it. Hope to see you in the next lesson. Goodbye! Here, I will show the parallel connection types using resistors in a direct current circuit. Components in an electrical circuit can be in series, parallel, or mixed connections. In this tutorial, I will demonstrate parallel connection. When we connect the 2 pins of the components, we have a parallel connection. In this connection, all resistors have the same voltage. Therefore, the current flowing through them is inversely proportional to the resistance values. A small current flows through a large resistor, and a large current flows through a small resistor. Since the same current flows from all lamps in series-connected lamps, when one of them explodes, the other does not light. Because the place where the exploding lamp is will be an open circuit, no current will flow from the other. Here, the solution is parallel connection. But it is not so with parallel connected lamps. Since all lamps have the same voltage, even if one of them explodes, the other continues to burn. Here we have given an example of a lamp as a load. It can be any circuit element instead of the lamp. In LED strips, all LEDs are connected in parallel. Even if one of them breaks down, the others continue to shine, or it is possible to use the sections separately when we cut from a point of a certain length. It doesn't make much sense to connect the LEDs in series, because each LED holds a certain voltage on it, it will cause a voltage drop. Therefore, it is ideal to light up multiple LEDs by connecting them in parallel. However, before doing this, we need to make sure that all the LEDs have the same power rating. In parallel circuits, we find the total resistance by adding the inverses of all resistances. If we name the resistors here as R1, R2, and R3, the total resistance will be 1 over RT equals 1 over R1 plus 1 over R2 plus 1 over R3. Total resistance is shown as RT. We can find the total resistance by adding the opposites of all the parallel resistances.